Okay, so quick recap. So last time we start talking about the GPU architecture, and we start with the execution, and we mentioned the concept of WAP, right, which corresponding to a single processor on GPU. So we said that the thread within the WAP are physically in parallel because they are already executed on a single processor, right? However, for the threads that's within the same block, but not in the same WAP, then they are only executed in parallel logically because they actually could be running at different time. Because they may run on different thingy processor, right? So there's no global synchronization across those thingy processors. Okay. So it's important to know whether your threads are within the WAP or not, because a WAP is the basic execution unit in on GPU. So almost all the optimization and those execution decisions are made in the unit of WAP. Okay, so the optimization we mentioned, normally you only need to consider the behavior of the threads within the WAP. Okay, and if it's across WAP, then basically maybe that optimization will not apply because they may not even run in parallel or run at the same time, right? Okay, so the concept of WAP is really important, and as we mentioned before as well, that the WAP is the basic unit, so it's also the basic unit for context switch on GPU. So any thread within the WAP has memory store, then the GPU scheduler will also context switch between the WAP. Okay, and because we might run multiple blocks and multiple WAPs on a single stream processor, so the stream processor will just context switch those WAPs among them. Okay. All right. So as long as try to fit up those Cindy processor and make sure we can utilize those computing power as much as we can. Okay. So that's why you can see the example below, right? Keep context switching between the WAP belong to different thread blocks. Okay. And every time there's a memory store, then the WAP or the GPU scheduler can context switch to another available active WAP. Okay. All right. So that's why we also mentioned the WAP divergent, right, or branch, right? We try to avoid branch in GPU, especially the branch within a WAP. Yeah, because for WAP they can only execute the same instructions at the same time. So if you have a branch and you want the threads within the WAP to do different instruction, then you will end up with execute both conditions and simply select the result at the end. So you actually do the work twice. Okay. All right. So on the other hand, right, if you can branch at the unit of a WAP, right, then even so you have a branch, you won't suffer from the WAP divergent problem. And so here is some example to show you this case. This may not be common, but if your computation somehow can be optimized in this way, then you will also gain some performance benefits. Okay? But like the example here, sometimes it's hard to do, and especially if you ask the threads to do different amount of computation. That's why we said that for most of the CUDA program, we want to make sure the load is balanced. Furthermore, we want to make sure, hopefully want to make sure all the threads execute the same instruction at the same time. So you will never suffer from the WAP diversion problem. Okay? Okay, so at the end, it's about know your right data pattern and dependency well, and then see if you can explore those patterns and avoid those performance degradation. Okay, and another technique, also kind of related to, more related to execution, right, is unroll the for loop. And the reason you want to unroll for loop on GPU is because for loop, right, you have a condition, right, after each iteration. So that means you have to perform some additional computation, right? So if you can unroll it, right, like so what we see over here, then you can reduce the the statement for checking the condition. So of course that can make your you can shorten your execution time, right? So unroll the for loop is always a way to optimize the performance. Okay. But of course, as you might know, the problem is how do I know how many loops can we unroll, right? Especially if the condition is determined at the runtime, then but your code is right have to compile in advance. So sometimes you cannot completely unroll the pipeline, right, or unroll the for loops. But you can somehow you can find a middle ground, right? For example, maybe you can unroll right 3 times only, right? And so you can reduce the amount of condition check by 1/3, right? Because you only check once for every 3 iterations. And of course, it's like memory padding, right? You will at the end, maybe you will do a few more additional iterations, right? But overall, maybe you can still achieve better performance, right? So it's again all depends on how well you know about your program, right? If you know the iteration will goes on between maybe 100 to 110, then you can unroll by 10 or even 20, right? And so only the last batch you might suffer from additional computation, right? Anyway, those are you can imagine that's how you can reduce some of the computation in GPU. Okay? All right. So of course, usually if you want to unroll our for loop, we don't just copy the code because you will easily cause some human mistake, right? So we have compilers to do that, right? You can simply use the compiler directive, very similar to what we have told for OpenMP, right? But this is a very general compiler directive for basically the regular C compiler. Okay, so you can have this unroll and a number follows that indicate how many loops, right? How many iterations you want to unroll. So it will just expand the code. So if here you say unroll 3, then that's the solution we see over here, right? The compiler will convert your code from this one to the one below, right? Okay. Okay, so yeah, if you have a lot of iterations and you know that you will go some for many iterations, you can try to unroll the for loop and see if that can reduce some of the computation time. Okay? And how many iteration to unroll is right performance tuning knob, of course. Okay? All right, and the last thing we want to mention about execution is the autonomic operation, because right for most of the parallel program, it's hard to avoid synchronization or share data access, right? As we have told for thread programming, we introduced a couple of synchronization or synchronization mechanism to address the race condition problem. We have lock, unlock, right, mutex lock in P threads, those kind of mechanism or library support solution, right? So for CUDA, it also support some of those instructions. It is called the autonomic operations. Okay, and basically, as you can imagine, what happened is you will ask the GPU to apply some lock on the shared memory content, and so he will force mutual exclusion on that memory content. Okay? So for example, we have right count plus plus, and for example, if we have all the threads to access this counter, they may all try to manipulate on this count variable. Then, and because this count is right stored on the shared memory, then we can try to declare it as a we can use the autonomic operation to manipulate this memory content. Then the GPU it has hardware logic to support that autonomic operation, so that lock and unlock will apply on those operations and make sure the operations are mutual exclusion among all the threads. Okay, and of course it's support by hardware instructions, so there's only limited autonomic operations are supported by GPU, and for example like addition, subtraction, max min, and so on and so forth, right? So you can see those are hardware autonomic operations or instructions supported by GPU. Okay, so you can see this is a use case for that. For example, we want to build a histogram, right, for some, say, data elements stored in an array. And then we can ask the threads, right, to scan through, right, or handle those data element in parallel, right? And depends on the color, we put, increment the count for that corresponding bin by 1, right? So at the end, we can, the bin will return the histogram of the data, right, of the data values. Okay, so because this bin, any bin could be accessed by multiple threads at the same time, so to avoid a race condition, we can apply the autonomic add, right, to avoid race condition problem. Okay, so this can make our code very clean, right, and correct. However, you can imagine the performance probably will not be too good, because as long as you have lock, then you basically convert the operation into a serialized manner, right? So you lost parallelism basically. Okay, so usually it will also cause significant performance degradation, unfortunately. Okay, right? So use it widely, right? You need to be wise on when to apply those operations, right? If you have too much contention on that shared variable, you should try to rewrite your code in other way. Okay, for example, how to compute the sum of an array. You can find some CUDA library to do that. Usually they don't implement in this way, like apply a autonomic, say, add, or aggregate on that variable, on the aggregated variable. Okay, usually they will try to use divide conquer strategy to preserve the parallelism, right, in your computation. Okay, so don't try to rely on those autonomic operation too much. Usually they are the performance usually won't be too good. Okay, all right, but still good to know. And in some case, if you don't expect the threads to access those shared data at the same time, then use autonomic operation can solve your problem easily, and solve it by hardware. So it could be even faster than your software coding. Okay, so that's it for thread execution. Okay, but more importantly is the memory, right? Memory is the important part for GPU and for our course. It's more important. Okay, And so we will officially start to introduce those memory, the memory architecture. Okay, those different memory layer we mentioned. Now we will look deeper to see how they are manipulated or accessed by your thread. Okay, and how you could allocate and manage the data on those memory layers. Okay. All right. So first of all, the memory hierarchy we have is including the highest level is the registers, right? As you can imagine, right, register is per thread scope, right? So every thread has a set of register. And we mentioned that the register actually is a physical thread. So every thread running on CD processor or on GPU has its own register set. Okay, so they can context switch very quickly. Okay, and the register, of course, is implemented as an on-chip memory to the string processor, and so it's very close to the CD processor. That's why they have low latency and high bandwidth. Basically, the fastest memory access you can have on GPU. Okay. And the next layer is the shared memory. We mentioned it before, right? So its access scope is per block, right? So every block has a shared memory. And so the space needs to be managed by the user and shared by all the threads within the thread block. Okay. And we also normally say it as a programmable cache, right? Because it's all up to the programmer to write the code to store and to load the content on the shared memory. And so it's completely managed by the programmer, by your CUDA code. Okay? So it's very critical for the programmer to utilize this shared memory. Okay? And this is also what you will exercise for your next CUDA lab, okay, which will be scheduled on this Thursday. Okay, we will, of course, talk about shared memory a bit more in today's lecture. Okay. All right, and the next level is the global memory. Okay, so of course it's the slowest memory, the lowest memory layer on GPU. Okay, because it's a off-chip memory, means it's an off-chip memory to the string processor. So you have to go through some connection channel between those two chips. So that's why the latency will be much slower than the register and the shared memory. Okay. By the way, shared memory actually has very similar performance to register. Okay. Although because it's on the also it's an on-chip memory. Okay. Just the data access scope is different between register and shared memory. Okay. But the performance are pretty similar. Okay. On the other hand, global is much slower and the bandwidth is also lower. And also, in principle, the data stored on global memory cannot be cached on the string processor. I said in principle because technology keep advancing. So according to the latest spec from some of those GPU vendor, they claim or they mention it is also possible they will cache some of the content from global memory, but uh, anyway, it's still much slower than the shared memory. Okay? But at least it's much faster than the bandwidth between the host and device. So of course, the bandwidth between host and device still the major bottleneck, the slowest one. Okay. And here we have a local memory. I will explain this later, but basically the local memory actually store the data from your register, or we should say from the local variable. Okay, so because for a function, right, for your CUDA program, when you write the kernel function, you can declare as many local variable as you want, right? However, on the CD processor or on the string processor, it can only assign limited registers for each thread. So you may not have enough space to hold those all the local variables, in the register. So when you run out of space, those local variable will be spelled out and stored on the memory chip, sent as the global memory. Okay, so it basically will occupy the same space and has the same performance as a global memory, but its content actually comes from local variable. Therefore, we code it as a local memory. So the local is referring to the variable, not referring to the hardware location. So it's not local to the core at all. Okay, so um, that's why you can see this DRAM memory space is used to store both the global memory and the local memory. Okay, all right. We will talk about this more later. Okay, and finally, the constant memory. We could also use it as optimization for CUDA code, because if your data is read only, you can store it on constant memory instead of the global memory. Because the constant memory is read only, so it will definitely be cached. Okay, if after you access it from the GPU core, it will be cached on the on-chip memory space. Okay, it doesn't show in this figure yet, but later on we'll see that we'll indicate it on the later slides. Okay, so the constant memory can be cached to the on-chip memory, so it will be faster if you try to reuse the data from constant memory. Okay? And as a matter of fact, there are many other more memory type of memory or different memory region you can use on GPU, like for example texture memory. But we don't introduce them because those memory usually is designed for graph processing, not for general purpose processing. So if you know their property and you know the API, you can also use them, but maybe they won't make sense for general purpose computing. You can access them, you can utilize them, but maybe you don't find any benefit from using them. Okay, but constant memory is different, right? So if our data is read only, then we can use constant memory to accelerate the data access time. Okay, without wasting the space on the shared memory. Okay, because shared memory space is also limited. Okay. All right. So as you can see, this is a complete mapping between your variable in your program space to the memory space on your GPU memory architecture. Okay. So as I mentioned, the local variable, right, declared and allocated inside your kernel function could be stored on registers or on local memory. And it is decided at the compiler time, decided by the compiler. Because of course, the compiler will try to use the register first. So so the compiler will do the address binding, okay? And it will try to bind those local variable to register. And if you run out of the register, then you will try to do the address binding to some location, some address on the global memory. But because it's stored the local variable, so the global memory that store the local variable is called the local memory. Okay. All right, and shared variable is simpler. It's of course it mapped to the shared memory. So shared variable mapped to shared memory. But this one is programmable, as we said. So how to manage shared memory space is very, very critical. And it's decided by the programmer. Okay. And finally, is the global variable, right? Means the variable that you want to be seen from the whole grid or from all the threads of your kernel, then you have to store it on global memory or the constant memory, right? If it's read-only, we will suggest you to store it on constant memory. Okay. If not, you have to modify, then you have to store it on global memory. Okay. Okay, so that's how your variables will map to the GPU memory hierarchy. All right, so then we will talk about start talking about each of those level in more detail. Okay. Okay, so the first one, the highest level is register. I already mentioned it quite a few, but we can see a bit more in this slides. Okay, so well, first of all, register is fast, right? You only need a few cycles to do the read and the write operations on it. Okay. However, it may suffer from the bank conflict problem. We will talk about this problem in the next lecture. And of course, one of the way to optimize your code is to avoid bank confliction of those registered assets. Okay, so you can make sure your registered assets is up to the ideal speed. Okay, but on the other hand, if you have bank conflict in your memory access pattern, then you might slow down your data access time. Okay, and another thing, another limitation for the register is it cannot be indexed. So that means it cannot handle array variables. So if you declare an array in the kernel function, then that variable will not be stored on register, no matter you have enough register space or not, because its register are not indexable. Okay, so that's why for most of the CUDA code, we try to avoid using array in the kernel function. If we use it, then the array usually is for shared memory. Okay, but if it's just local variable, then you will not try to use array to do that because you guarantee the data will be stored on the local memory, which is worse than shared memory, right? So why would you do that, right? Okay, so another problem is the space, right? You have as we mentioned, you have limited register sizes for each thread. And as a matter of fact, the size of register, the number of register available for each thread is depending on the block size. Okay, because for the stream processor, when he tried to allocate the register, is actually allocated by the thread block. Okay, so every thread block has a limited size of the register file. Okay, for example, maybe it's 100 register per thread block. So if you have 100 threads on that thread block, then each thread can only be assigned with one register. On the other hand, if you run a thread block with just one thread, then that thread can use up to 100 registers. Okay, so you can see to tuning the performance on GPU is quite hard because everything has a trade-off, right? You might think if I could increase my performance by increase my thread block, right? Because we can utilize more threads, so I have better parallelism, which is true. But if you have too many local variable, right, declared on or needed by each thread, then you may run out of the register file. Then you might some of the local variable will be spelled out to the local memory. Then you will suffer from slower memory access time. And as we know, for most of the GPU program, the performance bottleneck is on the memory access time, not the computing time. So if you keep increasing your parallelism, you might save your computation time, but you suffer from even worse memory access time. So at the end, maybe your execution time is increased, not decreased. Okay. All right, so this is the effect called register spelling, right? Means that if you don't have enough register, then your local variable or your local variable will be spelled out to the local memory, and you will suffer from the slow memory access time. Okay? So usually we want to control the number of threads of each block, or we should say the optimization is to minimize the register usage of each thread. It's always the right thing to do. Of course, one of the way to do that trade-off is you might use a fewer number of register, right? But you might need to, in order to use fewer number of registers, maybe you need to rewrite your code and to rely on more computation, right? Because some of the value you can recompute it, right, instead of store it. So that's a decision, right? Whether to store it on a register or you save the register by recompute it from your other results or from other register. So that's a trade-off, right? Recompute it or store it. And if you want to avoid register spelling, maybe you will need to recompute it instead of store it. But if you don't have register spelling problem, you can, right? Of course, store it in register and avoid some recomputation. Okay. And how do you know, right? How do you know you have a register spelling problem? It's very easy to find out. Remember, we mentioned that the CUDA code is compiled in two phases. You have the PTX code, right, in the middle. So you actually can dump the information because how many register is used is decided at the compile time. So after you do the compilation, you can actually pull out this information to check how many registers you use, how many variables are spelled out to the local memory. And then you can, based on that, to decide how to rewrite your program and to avoid register spelling. All right. Okay, so that's important. Okay. All right. The second layer is the local memory, right? Or I shouldn't say the layer, but as I mentioned, if it's spelled out, it goes to the local memory. Okay, so we already know what's a local memory. It's still a private area. No, it's a local variable, right? And it's stored on a private area that can only be accessed by a thread. Okay, so you don't have any synchronization problem. So for the local memory, it could be cached as well on the on-chip memory. Okay, but the detail depends on the hardware. Okay, it will be done automatically, not controlled by your program. Okay, although it's called the local, but as we said, it's actually stored on the global memory, the off-chip memory. So it's pretty slow. Okay. And whether the local variable is stored on the local memory or not is resolved by a compiler, as we said, and it could be cached. Okay. All right, so a bit more specific, this is where it could be cached, right? So again, usually have multiple level of cache, and details depends on the hardware, right? It's always changing, but usually the L1 cache for local variable is stored on the stream processor. So it could have, has a performance close to the shared memory or the register. Okay, but that's only when it is cached. Okay. And L2 usually, it has a layer of cache on the off-chip memory as well. You might think the performance is the same as global memory, so why bother to have this cache? But the benefit of cache is sometimes you can collect those reuse the data, right? So you can find those data faster. So somehow, usually, it can still accelerate your data access time. Okay. So still they have this off-chip cache for the local variable or for the constant memory. Okay. All right. So that's all those cannot be managed by your program. So I guess it's just good to know that what's underneath it. Okay. And this example, right, to emphasize that, to see if you can identify whether the variable will stored on register or on local memory, right? So you can see like here, the IJK, they are local variables, so they should be stored on register. But if each thread can only assign with one register, then unfortunately, only one of the three will be stored on register. Okay, and you can check that, as we said, from the compiler information. Okay, and A10, those are arrays, so unfortunately, all those needs to be stored on local memory. And that's why we don't recommend to write a code like this. Okay, you should try to avoid it. Okay. And also another thing is for the array, right? Any array in CUDA code, in kernel function, they do not allow you to, they only allow static array. Okay? Because we said GPU is purely managed, almost purely managed by hardware. So it cannot handle those dynamic logic, or that those complex logic. It will makes the hardware too complicated. So those array needs to be static allocated. So you cannot write a code like this. Okay. So you probably won't even pass the compilation. Okay. All right. So it's all those are the limitation for GPU programming. All right. So we have a 10 minutes break. So let's have a 10 minutes break and we come back at 4:30 and we will introduce the rest of the memory architecture, including the shared memory and the global memory. Okay. And finally, we will introduce occupancy, which is another performance or span evaluation metrics to determine whether you use those memory architecture properly. Okay. All right. So let's have a break. And if you have any question, you can feel free to ask now.